Welcome everyone. We are discussing permutation. Through this video, today I will discuss permutation of things when all the things are not different. So, theorem. What is the relevant theorem? Let there are n things of which p numbers are of first kind, q numbers are of second kind, r numbers are of third kind, and rest are different. Rest are different. Then arrangements or permutation, arrangements of these n things taking all at a time, equals to total number of things factorial, factorial p, factorial q, factorial r. So total number of things, factorial of total number of things by repeated objects or articles. For different things, factorial 1, factorial 1, factorial 1, so it will be 1, so there is no contribution for different thing. So this will be our working tool. N things, P of which are first kind, Q of which are second kind, R of which are third kind. So first of all, I will take a simplest problem. Find number of arrangements by taking all letters of Shalom. SLOON. Number 2, commerce. Number 3, again. These are of 1 marks. Simplest. So look, problem number 1. So look, letters are S, A, L, N. So O, this is repeated 2 times. Total letters 6. You have to write this one, total letters equals to 6, of which O2 and rest are different. Rest are different. So total number of permutation. So total number of permutations or arrangements. Obviously taking all at a time. So factorial 6 by factorial 2 by factorial 2. So this is 360. Only O is repeated factor. So total by factorial 2, 360. Similarly, suppose again Again. So it is factorial 5 total, and look, A repeated 2 times. So this is 120. So total number of things by factorial of repeated article. Now we consider problem involving this theory but with some restriction. So same type of problem that of the previous video. Here articles are repeated articles. Now we consider a problem where restriction is given. Find the number of arrangements of the letters of the word saloon if two O's come together. Number 2, two O's do not come together. So same technique we shall use, that of earlier class. So we consider two O's as a single one. So look, total 6 letters. 6 letters. 2O and S A L. So these are the letters. 2 O's are together. So what is our rule? Considering 2 O's as a single entity, or single one, we have 1 plus 4 equals to 5 letters. Look, out of these 5 letters, this is one letter, no repetitions. So they can be arranged in factorial 5 ways. Now 2 O's can be arranged in factorial 2 are same, that is 1 O's. So look, 2O, so no difference, that is why this is 1 O's, and by the formula factorial 2 by factorial 2. Therefore, by FPC, number of arrangements in which 2 O's are together equals to factorial 5 into factorial 2 by factorial 2, so 120. In case of allied letters, no need of this part because it will be always 1. So 120. And number 2, 2 O's do not come together. So same procedure, we will find number of permutation without any restriction. Then number of permutation in which 2 O's are together. So their difference will give no 2 O's will be together. So look, number of arrangements in which no 2 O's are together equals to total permutation total arrangements minus number of arrangements, number of arrangements in which two ways are together. So factorial 6 by factorial 2, this is total permutation. This equals to factorial 6 by factorial 2 minus factorial 5. So 360 minus 120 equals to 240. So same procedure that of earlier video. Here there are some alike letters or members. Next, now exactly same problem. Find number of arrangements of the letters of the word Mississippi in which 4 I's do not come together. 4 I's do not come together. So total letters 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So total letters equals to 11. 4 S's, 4 I, 2 P's and 1 M. So total number of arrangements without any restriction, arrangements equals to factorial 11 by factorial 4, factorial 4, factorial 2. This is total number of arrangements. Now we consider number of arrangements in which 4 I's are together. So if 4 I's are together, we consider 4 I's as a single one. So considering 4 I's as a single entity, single one, total number of letters equals to 11 minus 4. 4 I's, now we consider this 4 as a single one. So 11 minus 4 plus 1, so 8 letters. So they can be arranged in factorial 8 by factorial 4 into factorial 2 ways. Because there are 4 S's and 2 P's. So that is why we are getting this one. Now 4 I's can be arranged in factorial 4 by factorial 4. That is one way. So no need of writing it. So number of arrangements in which 4 I's are together. Factorial 8 by factorial 4 into factorial 4 and 4I factorial 4 by factorial 2 ways. So we are getting factorial 8 by factorial 4 into factorial 2 and 4I as factorial 4 by factorial 4, this one. So number of arrangements in which 4 I's do not come together equals to total arrangements factorial 11 by factorial 4 into factorial 2 into factorial 4 minus factorial 8 by factorial 4 into factorial 2. So, solving expanding factorial, you get result. So, same procedure, only here some letters are alike. Now we consider one more problem. Find number of 7-letter words that can be formed using letters of the word success such that two S's, two C are together, but two S's are not together, two C's. So this is slightly different that of earlier. So look at the language. Two C's are together. So what is our rule? 2C as a single one. So 2C as a single one. Then one is U. This is S. U, 2C, other than S, you get E. How many S's? No two S's are together. So S3. So we consider these two C's as a single entity, single one, and U and E. These two C, U and E, can be arranged in a row in how many ways? Factorial 3 ways, not by factorial 2, because we are considering these two C's as a single entity. Now how many gaps? 1, 2, 3, 4. 4 gaps. If we place 3 S's in 4 gaps, then no two S's are together. So this is our required condition. So what is the first one? Considering two C's as a single entity, C, U, E can be arranged in a row, in factorial 3 ways. Mind it, 2C, this is considering as a single letter. So this will be the figure, factorial 3. Now there are total number of 4 gaps. If we place 3 S's in 4 gaps, then no two S's are together. So this can be done in 4C3 ways. 4C3 ways, because these 3 S's are alike. Or actually, if you use permutation, it will be factorial 4 by 4p3, 4 gaps and 3 letters, and these 3 S's are alike. That is why it is 1 by factorial 3. So look, 4 gaps. So our formula is 4p3. But here 3 S's are of same type. So you have to divide it by 1 by factorial 3. Or you can use 4c3. 4c3, 4 gaps. These 3 letters are alike. That is why this is 4c3. You learn later in case of combination. Now, from permutation, you can use this one. And using combination, since letters are alike, this is 4c3. So, use FPC. By FPC, number of required arrangements, that is, CAs are together, but no 2 S's are together, equals to factorial 3 into 4p3 into 1 by factorial 3. So 4p3, so this is factorial 4 by factorial 1, so 24. Answer is 24. So this is slightly different. 2 CAs are together, but all the S's are not together. So you practice this type of problem. Now next one. Next problem. In how many ways 5 different subjects be arranged in 6 periods in a class? A class has how many periods? 6 periods. 1, 2, 3, 4, 5, 6. And how many subjects? 5 subjects. Suppose Bengali. Suppose English, math, physics, chemistry, bios. 5 subjects and 6 periods. So look, obviously there will be a period in which you have to repeat one subject again, because number of period is 6, number of subject is 5. So if is repeated again, then what is the total number of selection? So factorial 6 by factorial 2. Factorial 6 by factorial 2. Why factorial 6 by factorial 2? Because English period is repeated. Now similarly, you can repeat the another one also. So suppose if mathematics is repeated, then it will be factorial 6 by factorial 2. So similarly, for 5 such subjects, there will be a repetition. So look, number of periods equals to 6. Number of subjects equals to 5. Therefore, one subject must be repeated. If English is repeated twice, number of arrangements factorial 6 by factorial 2. So similarly, mathematics, physics, chemistry and biology may be repeated. So total number of arrangements, 5 into factorial 6 by factorial 2. Factorial 6 by factorial 2 5 times, that is 5 into this. So this is 5 into 360. 1800. So this is most important problem also. So 5 subjects, 6 periods. So one subject must be repeated. That is why we are getting factorial 6 by factorial 2. Now we consider another type of problem by repeated articles. How many numbers greater than million can be formed by using the digit 4606 746 greater than million? By using these digits, so 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7. Unit, tenth, hundred, thousand, 10,000, lakh, this is million. So how many gaps? 7 gaps. 7 gaps. So 6 3 times, 4 2 times, 0 or 7 1 time. So 7 gaps and 7 letters. So 7 gaps can be filled by 7 digits in factorial 7 by factorial 3 into factorial 2 ways. Factorial 3 into factorial 7 by factorial 3 into factorial 2 ways. But look, out of these ways, there are some cases in which 0 occupies first place, that is million place. So look, if 0 occupies million place, then this is not of 7-digit number. For example, 1 to 0, this is 3 significant number. But 0, 1, 2 is not 3 significant, this is 2. So this is total weights. But there are, so these includes some cases in which 0 occupies first place, but they are not of 7-digit number. So we have to delete these. So taking 0 at 7th place, taking 0 at first place, the remaining 6th place can be filled by factorial 6 by factorial 3 into factorial 2 ways. So these are total and these are 0 at first place. Therefore, seven-digit numbers, that is number greater than million, equals to factorial 7 by factorial 3 into factorial 2, factorial 6, factorial 3 into factorial 2. So simplifying, we get result. So these are problem using digits and earlier are using letters. So through this video today we have solved some problems, that is problems of permutation when there are repetition of numbers, repetition of digits. So in the next class I will discuss some more topics of permutation. Thank you for today.